All right, so I'm going to just review some important theorems from calculus, which are going to be relevant in our later lectures. Okay, so the first one, which is going to be of relevance, is what's called the mean value theorem. Okay, so the mean value theorem states the following, that if you have some function f, which is continuous in the interval from a to b, right? So again, it's like that means that f is continuous on the interval, on the closed interval from a to b, right? And f is sort of differentiable in the open interval from a to b, right? So f is differentiable. Then there exists a number c in this interval from a to b, right, such that the derivative at this point c is equal to the secant, sort of the slope of the secant line. Okay, so f of b minus f of a over b minus a. So let's try to visualize this. All right, so if you have sort of the x and y plane, okay, and you have some function f here, okay, and you have some points a and b, then there's a line which joins the point a comma f of a with the point b comma f of b. All right, so this is a secant line, and this secant line has a slope which is given by this right-hand side. And the claim then is that there exists at least one point in the interval, in the interior of the interval from a to b, right, whose derivative of f at one or more points is has the same slope as this. Sorry, the derivative is equal to the slope of this secant line. Okay, and here you can sort of see that there are 2 points which have this property. It's one here, and then there's one here, right? So this is a C1, and this is C2. So there exists at least one point in this interval such that this condition holds, and this is what is called the mean value theorem. Okay, all right. And then the next thing, it's like which we're going to use, it's what's called the intermediate value theorem. Okay. Okay, so here, if f is continuous, okay, C0, right? So that's continuous in the interval from a to b, and k is any number between f of a and f of b, then the claim is that there exists a number c in this interval from, okay, so c is an interval, okay, so, all right, so if k is a value between a and b, then there exists a number c in this interval a to b for which f of c is equal to k. Okay. All right. So again, if you have some function f of x, okay, and there's two f values, fb and fa at the endpoints, then if you choose any k, it's like in this interval from fa to fb, if I choose any value, k, then there is some point, it's like in this continuous function, right, for which f at that point c is equal to this k. All right, so for any k, it's like there's at least one point that's like an interval from a to b. All right, well, let me sort of back up. So if you choose k to be any value between fa and f of b, there is at least one point in the interval from a to b, and we call that point c, such that the value of f at that point c is k. Okay, so let me sort of just give you one example of where this is used. It's like later on in the course. So one of the things that we're going to talk about later on in the course are root finding methods. So these are ways of finding the zeros of a function, and the function is assumed to be continuous, basically in order for that problem to be sort of well posed. All right. And there's this idea known as bisection, and with bisection, what it is that if it happens that if the function changes sign in an interval from a to b, for example, which is to say that f at a is one sign and f at b is another sign, so that the product of f of a and f of b is negative, or strictly negative, right, then that means that since one of them is positive and one's negative, 0 is somewhere in between f of a and f of b. And so by the intermediate value theorem, there has to be a root of the function f somewhere between a and b, so long again as f at a and f and b have different signs. Okay, so this is sort of one example of where we're going to take advantage of this intermediate value theorem. Okay. So, all right. And then I should also sort of introduce a weighted version of the mean value theorem for integrals. Okay. So the third one is a weighted mean value theorem for integrals. Okay, all right, so let's suppose that f is continuous. Again, f is c0 in the interval from a to b, and g of x does not change sign. So g of x is going to be our weight. On this, so, and we don't want the weight to change sign in the interval from a to b. Okay, so if you have those two conditions, then the weighted mean value theorem for integrals states the following. Then there exists a number c in the interval from a to b with the property that the integral from a to b of f of x g of x dx is equal to f at this point c, the integral from a to b of g of x dx. Okay. All right. So that's the weighted mean value theorem. So you might ask how this relates back. It's like to the mean value theorem. Okay. So let's look at a special case of this. Special case. So the special case is when g of x is just identically 1. Okay, so g of x is identically 1. Okay, so in that situation, this integral theorem, well, g of x identically 1 satisfies the condition that it doesn't change sign at the interval from a to b. So we're good there. So we can go ahead and apply this theorem. All right, so this gives you the integral from a to b of f of x, and then g is identically 1. I'm just going to drop that. dx is equal to f of c, the integral from a to b of 1 dx. And the integral of 1 dx is obviously just b minus a. So this is f of c b minus a. All right, so this says that f of c is equal 1 over b minus a of the integral from a to b of f of x dx. All right, so there exists c interval from a to b such that this condition holds. Okay, so this is the average value of the integral in some sense. This is the average value. Okay, all right. So how do we recover the sort of the mean value theorem? Okay, so instead of f, it's like I'd replaced f with its derivative. I would have f prime of c. Okay, so f prime of c is equal to 1 over b minus 8 integral from a to b of f prime of x dx. And then by the fundamental theorem of calculus, right, that's just going to be 1 over b minus a, f of b minus f of a, right? So that's how it's related back to the usual mean value theorem. You know, when you do this, when you replace f by f prime, it's like you're basically assuming that f itself has higher regularity, right? So, okay, so let me rephrase that. Okay, so yes. So in order to replace f by f prime, we have to have f prime be c0. So basically that means that in order for this theorem, in order for this equation to hold true, it's like from the weighted mean value theorem, you have to have that f be c1, right? In not just the open interval, but the closed interval. So that's a slightly stronger condition. It's like then what we had, it's like with the usual mean value theorem, okay? But yeah, anyway, so that's sort of the reason why there's slight technical differences in the assumptions, if you will. It's like, and then sort of in the formal statements about whether this interval is closed versus open. But more or less, it's like you sort of see that modulo those technical issues, the expression you end up getting is what you would expect from the usual mean value theorem. Okay. So in any case, it's like what's going to happen is that we're going to take advantage of these theorems. It's like both in terms of constructing numerical methods as well as analyzing them, as we'll see in a little bit. So let me just stop here for now.